Our galaxy could have been a cosmic donut. This is not a fantasy, but a real type of structure that exists in the deep universe, known as a ring galaxy. They are some of the rarest and most mysterious shapes a galaxy can take, cosmic oddities that defy our basic understanding of how the universe builds things. By the end of this journey, you will understand 25 of their strangest phenomena, secrets that challenge the very laws of physics as we know them. We will explore perfect cosmic hoops that should not exist and galaxies pierced by rings of fire. What is the most beautiful cosmic mystery you have ever seen? Gaze into the cosmic eye of Hoag's object. It is the definition of celestial perfection, a stunningly symmetrical ring of brilliant blue stars encircling a golden, ancient core, separated by a seemingly empty gap of dark space. This is not a gentle spiral or a chaotic blob. It is a near-flawless circle suspended in the void. The immediate mystery is how such a perfect structure could form at all. Our standard story of galaxy evolution involves messy mergers and gradual winding, but Hoag's object presents a geometry so clean it feels designed. The leading theory points to a cataclysm, a smaller galaxy piercing the heart of a larger 1 billion of years ago. The gravitational shockwave would have sent stars rippling outward in a circular wave, like a stone dropped in a galactic pond, leaving behind a ring of frantic star formation in its wake. Yet here lies the deeper puzzle. Hoag's object floats in profound isolation. Astronomers have searched its quiet neighborhood and found no likely culprit, no nearby galaxy that could have been that stone. This leaves us with unsettling alternatives. Perhaps the ring was born from a massive internal instability, a sudden rearrangement of the galaxy's own stars and gas. Or maybe our understanding of galactic collisions is incomplete, and the evidence of the intruder has long since faded from view. Whatever the cause, Hoag's object stands as a serene, beautiful rebuke to our models, a perfect cosmic hoop whose origin story remains frustratingly, wonderfully blank. But perfection is not the only shape a ring can take. Some are born from violence so extreme it twists a galaxy into a new dimension. Consider NGC 660, a galaxy that looks as if it has been impaled by a luminous cosmic spear. This is a polar ring galaxy, a structure so bizarre it defies our two-dimensional expectations of how galaxies should spin. At its heart lies a fairly ordinary lenticular galaxy, a disk of old stars. Yet encircling it, not in the same plane but at a perfect 90-degree angle, orbits a massive ring of gas, dust, and young blue stars. Imagine a dinner plate spinning on a table, and then a glowing hula hoop spinning vertically around its edge. That is the impossible geometry of NGC 660. This perpendicular ring is almost certainly the ghost of a cosmic crime. Billions of years ago, a smaller, gas-rich companion galaxy ventured too close. It was captured, torn apart by immense tidal forces, and its scattered remains were caught in a gravitational dance. Instead of merging into the main disk, this captured material settled into a stable orbit around the galaxy's poles, tracing a path dictated by the larger galaxy's invisible halo of dark matter. This is why polar rings are more than just spectacular oddities. They are unique three-dimensional probes. The stars and gas in the ring are like tracers, mapping the gravitational field in a way we can rarely see. By observing how the ring moves, astronomers can chart the distribution of the unseen dark matter that holds the entire bizarre structure together. NGC 660 shows us that a galaxy is not just what we see in visible light. It is a complex gravitational sculpture, and sometimes the most violent collisions leave behind the most revealing shadows. Yet the most famous and dramatic example of this cosmic violence is written across the face of the Cartwheel Galaxy. This is not a serene eye or a tilted halo, but a full-blown cosmic bullseye, a target painted in starburst fire across 150,000 light-years. Its appearance is unmistakable, a brilliant inner ring of newborn stars, a dusty gap, and then a vast, sprawling outer ring that defines the galaxy's very edges. This is the textbook example of a collisional ring galaxy, and its story is one of unimaginable impact. Roughly 400 million years ago, a smaller spiral galaxy, perhaps one-third the size, made a near-perfect bullseye shot. It did not glance off or slowly merge. It plunged directly through the heart of what was then a normal spiral galaxy, like a bullet through smoke. The gravitational shockwave from this head-on collision was catastrophic and beautiful. It sent a titanic ripple of compressed gas and dust racing outward from the center at supersonic speeds. Picture dropping a heavy stone into a still pond, watching the circular wave expand from the point of impact. In the cartwheel, that wave is made of interstellar material, and where it travels, it triggers frenzied star formation. The bright inner ring marks where the first, most intense wave of compression ignited billions of stars. The even larger outer ring is a secondary ripple, a later echo of the same event, creating a vast circle of stellar nurseries on the galactic frontier. The smaller intruder galaxy, having delivered its devastating blow, can still be seen fleeing the scene, a guilty witness receding into the darkness. The entire system is a slow-motion snapshot of a single, transformative moment, a galactic accident frozen in time that shows us how the most destructive events in the universe can also be the most creative, forging rings of new light from the ashes of a collision. But sometimes the universe does not settle for a single perfect ring. It creates echoes. Drifting in the void near the Large Magellanic Cloud is a galaxy that seems to have been struck twice, AM 0644-741. From our distant vantage point, it presents a breathtaking and baffling sight, a brilliant inner ring of furious star formation wrapped within a larger, ghostlier outer ring. It is a cosmic target with two concentric circles of light, a more intricate puzzle than the cartwheel's singular bullseye. The inner ring is a tight band of intense blue, a stellar nursery ignited by a powerful wave of compression. Surrounding it, further out, lies a second, broader ring, fainter and more diffuse, as if the first shockwave triggered a secondary, slower ripple. This layered structure suggests a collision of extraordinary complexity. Astronomers believe the intruder galaxy did not make a simple, direct plunge. Instead, its trajectory was likely a glancing blow, or perhaps it possessed its own significant mass and structure, interacting with the victim galaxy in a prolonged gravitational dance. This messy encounter would have sent not one, but multiple density waves racing outward through the galactic disk at different speeds and intensities. Think of it not as a single stone dropped in a pond, but as a handful of gravel tossed in at an angle. The resulting waves overlap, interfere, and create a pattern of rings within rings. Modeling such an event is a monumental challenge for astrophysicists. It requires simulating the precise angle, speed, and mass of two entire galaxies, along with the chaotic behavior of their gas and dark matter. AM 0644-741 is a natural laboratory for galactic dynamics, showing us that these collisions are not simple billiard ball hits. They are messy, drawn-out affairs whose final forms depend on a delicate and violent ballet of forces, leaving behind layered signatures in light that we are only just beginning to decode. These galactic echoes are not always neat concentric circles. Some rings are born from collisions so chaotic they twist the fabric of the galaxy itself. Look at NGC 4622, a galaxy that appears to be spinning in two directions at once. Its outer spiral arms sweep gracefully in one direction, suggesting a clear rotation for the entire system. Yet nestled within, closer to the core, are faint inner rings that seem to swirl the opposite way. It is as if the galaxy contains a second, smaller galaxy rotating backwards inside it, a cosmic gear spinning against the flow. This counter-rotating configuration is a profound puzzle, for it challenges a fundamental principle. In a typical, isolated galaxy, all the stars, gas, and dust share a common direction of spin, a legacy of the original cloud that collapsed to form it. For one part to spin backward implies a violent history of invasion and theft. The leading theory points to a very specific kind of galactic meal. Billions of years ago, NGC 4622 likely consumed a smaller companion galaxy. But this was no simple merger. The victim galaxy approached from a particular angle, with its own significant store of gas and stars spinning in the opposite direction. As it was torn apart and absorbed, this counter-rotating material did not simply blend in. Instead, it settled into its own distinct orbit within the larger galaxy, like a river of upstream swimmers suddenly flowing into a downstream current. The gravitational forces involved are incredibly complex, imparting a twisted angular momentum that warps the entire system. For astronomers, galaxies like NGC 4622 are not just curiosities, they are critical stress tests. Simulating such a precise merger, one that creates stable, counter-rotating rings without utterly destroying the host galaxy, pushes our computer models to their limits. Each new observation of these warped rings forces a refinement of the physics, teaching us that a galactic collision is never a simple addition of mass. It is a turbulent mixing of histories and spins, a cosmic dance that can leave a galaxy permanently, beautifully confused about which way to turn. The violence that creates a ring galaxy does more than just rearrange stars, it unleashes a firestorm of creation. In the chaotic merger known as 2ZW96, we see this principle pushed to a terrifying extreme. This is not a serene, settled ring, but a lopsided, tangled wreck of two galaxies caught in the act of colliding. At its heart, glowing with an almost painful intensity, are two brilliant knots of raw light. These are not single stars, but colossal stellar nurseries, regions of star formation so intense they outshine the entire cores of most normal galaxies. Astronomers call this a starburst, but that term feels too gentle. This is a star-forming frenzy, a cosmic forge operating at maximum capacity. The ring structure itself is the engine of this chaos. As the two galaxies intertwine, their mutual gravity acts like a cosmic funnel, violently channeling vast rivers of cold gas and dust into dense, swirling reservoirs along the emerging ring. Within these reservoirs, the conditions become unimaginably harsh. Gas clouds collapse under their own weight at a rate hundreds, even thousands of times faster than in our peaceful Milky Way. Stars are not born here individually, but in frantic, screaming clusters. They form across the entire spectrum, but it is the most massive, brilliant, and short-lived stars that dominate the scene. These blue giants burn their nuclear fuel in a few million years, a cosmic blink before exploding as supernova. Their deaths, in turn, blast the surrounding gas with shockwaves, triggering further collapse and igniting the next generation of stars in a runaway chain reaction. The luminous knots in 2ZW96 are these chain reactions made visible, hotspots of birth and death so concentrated they can be seen across vast intergalactic distances. This ring of fire shows us the dual nature of cosmic violence. The same gravitational forces that tear galaxies apart also compress the raw materials of creation, lighting temporary beacons so fierce they briefly outshine everything else in the universe, a spectacular but ultimately fleeting blaze of glory. This brilliant ring of fire raises a deeper, quieter question. Why is the center so empty? In galaxies like Hoag's object or the cartwheel, we see a stark contrast, a luminous core of ancient stars, a dark and seemingly barren gap, and then the blazing ring of youth. This dark gap is a universal signature of ring galaxies, and its existence is a clue to the violent physics that shaped them. The leading explanation comes from the density wave theory, the same idea that explains the spiral arms in galaxies like our own. Imagine the shockwave from a galactic collision racing outward. This wave is not made of moving stars, but of moving conditions. It is a region of compressed gas and dust, a cosmic traffic jam traveling through the galactic disk. As this density wave passes, it squeezes the interstellar material, triggering the collapse of gas clouds and the ignition of new stars. The ring we see is simply where this wave is located right now, a temporary zone of frantic creation. But the wave moves on. The stars it leaves behind are massive and bright, but they are also short-lived. They burn out and die within a few tens of millions of years. Meanwhile, the gas and dust that fueled them has been either used up or pushed further outward by the wave's passage. This leaves the region behind the wave, the gap between the ring and the core, stripped of the raw materials needed to make new stars. It is a sterile zone, a wake of stellar depletion. There is another, more subtle possibility at play, involving the delicate balance of pressure. After the initial collision, the central regions of the galaxy may be left in a state of heightened turbulence or bathed in intense radiation from the remaining core. This chaotic environment can prevent the calm, cold collapse necessary for starbirth, effectively putting the central gas on hold. So the dark gap is not truly empty, it is likely filled with older stars and diffuse hot gas. What it lacks is the cold, dense nurseries required to spark new stellar life. It is a fossil record of the wave's path, a silent announcer that proclaims the fire has moved on, leaving only embers and ash behind. This leads us to wonder, if the ring marks a wave of creation, what happens when that wave finally reaches the edge? This frozen wave of starlight offers us something extraordinary, a galactic clock. Because the ring structure is not static, it is a propagating event. It allows astronomers to do something rarely possible. They can read stellar history like the rings of a tree. In a perfect ring galaxy, the outer edge of the luminous band marks the very forefront of the shockwave, the place where star formation is happening right now, or at least within the last few million years. Just inside that brilliant edge, the stars are slightly older, perhaps 10 or 20 million years old, having ignited as the wave passed through that region earlier. And as your gaze travels further inward toward the galaxy's core, the stars you encounter become progressively more ancient. What we are looking at is a single, coherent timeline of stellar evolution laid out in spatial order. It is a fossil record written in light and distance. In a typical spiral galaxy like our Milky Way, star formation is messy and ongoing across different arms, making it incredibly difficult to compare stars of different ages directly. They are all jumbled together, but here, in this rare ring, the universe has provided a clean laboratory. By studying the chemistry, brightness, and types of stars at different points along the radius, from the blue infants on the outer rim to the yellow middle-aged stars further in, and finally the red ancient stars near the core, scientists can construct a precise sequence. They can observe how star clusters change as they age, how supernova explosions from earlier generations enrich the gas that will form later stars, and test theories about how quickly stellar populations evolve. This single structure acts as a time capsule, preserving distinct chapters of its own violent history in concentric shells. It lets us watch billions of years of cosmic growth and change, not by looking back through time at different galaxies, but by looking across the face of one. This galactic clock, however, has a missing piece of evidence. In the courtroom of the Cartwheel Galaxy, we have the victim and the perfect crime scene, but the prime suspect has seemingly vanished. The small intruder galaxy that delivered the bullseye shot 400 million years ago is no longer at the scene. It is a ghost, a cosmic perpetrator that has fled, leaving behind only the spectacular ring as its calling card. Its absence is not a flaw in the story, but a crucial part of the physics. So where did it go? Astronomers have three leading theories, each a different fate written by gravity's relentless hand. The first possibility is absorption. The smaller galaxy, already damaged from its daring plunge, may have lost too much speed. After passing through the core, it could have been gravitationally captured, swung back around, and finally consumed by the larger galaxy it had just wounded. Its stars and gas would have been scattered and assimilated, its identity erased within the body of its victim, a truly final merger. The second, more dramatic fate is escape. The collision may have been a perfect gravitational slingshot. If the intruder came in at just the right angle and speed, the immense gravity of the larger galaxy could have flung it away on a hyperbolic trajectory like a stone from a catapult. It would now be a high-velocity rogue speeding through intergalactic space, forever exiled from the scene of its transformative crime. The third possibility is hiding in plain sight. The brilliant starburst rings and the luminous core of the cartwheel create an overwhelming glare. The faint, stripped remnant of the intruder galaxy, now just a skeleton of its former self, could be lurking within that glow, camouflaged by the very chaos it created. Pinpointing this ghost is more than a cosmic detective game. It is essential for reconstructing the exact conditions of the impact. The intruder's mass, its angle of approach, and its speed are the initial variables that determined everything about the ring we see today. Without finding it, or at least confirming its fate, our understanding of the event remains an incomplete equation. This missing perpetrator reminds us that the universe is a dynamic arena of motion and consequence, where the actors in a drama billions of years old may have long since exited the stage, leaving us to decipher the story from the scars they left behind. The ghost of a perpetrator is one thing, but what about the ghost of an entire meal? The universe presents us with an even more puzzling scene. A galaxy that seems to have digested a star-forming feast but left the bones on the outside. Meet the Skewered ring galaxy, a phenomenon where a perfect, delicate ring of cold gas and young blue stars encircles a massive, smooth, and ancient elliptical galaxy. This pairing should not exist. An elliptical galaxy is the cosmic retirement home for stars, a vast, football-shaped swarm of old, red suns that orbits in random directions. It contains almost no cold gas, the essential ingredient for making new stars. Its environment is hot and turbulent, utterly hostile to the calm, cold collapse needed for stellar birth. Yet here, wrapped around this sterile giant, is a vibrant, narrow ring of youth, a cosmic wedding band of creation placed upon a hand of dust. How did this ring of life find itself around a galaxy of quiet death? The leading theory is one of galactic cannibalism on a grand scale. Billions of years ago, this giant elliptical likely consumed a much smaller, gas-rich companion, perhaps a spiral or irregular dwarf galaxy. In most mergers, the captured gas would fall chaotically into the center, triggering a brief central starburst before being used up. But in these rare, precise encounters, something different happened. The victim galaxy's gas was stripped away gently and in just the right amount, like peeling an orange in one long spiral. Instead of plunging inward, this stolen gas settled into a vast, stable orbit far from the chaotic core. There, in the quiet outskirts, it could slowly cool and condense, eventually igniting the chain reaction of star formation we see as the ring. This makes the Skewered ring a fossil of a very specific kind of violence, a slow and delicate feast rather than a catastrophic collision. The ring is the last breath of a consumed galaxy, a final, beautiful structure built from its remains, orbiting the giant that destroyed it. It is a testament that even in the act of galactic destruction, new and unexpected forms can be born, hanging like a luminous halo around a silent, sleeping giant. But what happens to a ring of fire when its fuel runs out and its light begins to fade? The universe may hold the answer in structures so faint they hover at the very edge of invisibility. These are the ultra-diffuse rings, the ghostly afterimages of cosmic violence. Imagine a ring galaxy stretched thin across an immense volume of space, its stars so widely scattered that their combined glow is barely a whisper against the blackness of the void. These are not brilliant hoops of blue giants, but pale, ethereal halos of ancient red dwarf stars, relics of a star-forming frenzy that burned out eons ago. Detecting them pushes our most powerful telescopes to their absolute limits, a game of finding cosmic smoke long after the fire has died. Their existence presents two haunting possibilities. The first is that they are the final, fading chapter in the life of a collisional ring like the cartwheel. After the initial starburst ring blazes for a few 100 million years, the massive stars die in supernova. The remaining gas is expelled or used up, and star formation grinds to a halt. What remains is the underlying population of longer-lived, smaller stars that were also born in the ring. Over billions of years, gravitational interactions slowly puff this population outward, dispersing the stars into a wider, ever dimmer band. The once tight, brilliant ring becomes a vast, faint smoke ring, a ghost of its former self. The second possibility is even more subtle. Perhaps these ultra-diffuse rings were never bright to begin with. They could be the product of extremely gentle, grazing interactions between galaxies, where the tidal forces were just strong enough to stir the stars into a loose ring shape without ever compressing the gas enough to trigger a major starburst. It would be a whisper of a collision, leaving behind only a subtle rearrangement of old stars. If either or both of these scenarios are true, the implications are profound. It means the spectacular ring galaxies we easily see, like Hoag's object and the cartwheel, could be just the tip of the iceberg. For every brilliant ring, there might be dozens, even hundreds of these ghost rings drifting unseen in the darkness. Our current census of galactic interactions, based on what we can readily detect, could be a dramatic undercount. The true history of the universe may be written not only in brilliant flashes of creation, but in these vast, silent halos, the faint and fading signatures of encounters that happened when the cosmos was young. Even the faintest ghost ring is held together by forces we cannot see. Beyond the light of stars and the pull of gravity, another hidden architecture shapes these cosmic structures, a web of invisible lines of force. Within the chaotic crucible of a colliding ring galaxy, magnetic fields are not passive observers, they are active participants, twisted and amplified into a formidable maze. Picture the immense shockwave of a collision racing through the galactic disk. It does not just compress gas, it also squeezes the galaxy's existing, diffuse magnetic field, stretching and folding it like cosmic taffy. This process, known as turbulent dynamo action, can intensify the magnetic field's strength by 100-fold or more along the leading edge of the ring. The result is a magnetic skeleton woven directly into the ring of fire, a complex network of force fields aligned with the frantic streams of gas and newborn stars. This invisible maze has profound consequences. Magnetic fields exert pressure. They can support clouds of gas against their own gravity, potentially slowing or even preventing the collapse that leads to new stars. In this way, the very forces that help create the ring's starburst might also act as a subtle brake, regulating the frenzy of creation. Furthermore, these amplified fields become superhighways for cosmic rays, the ultra-high energy particles accelerated by supernova explosions. The tangled magnetic lines act as guiding rails, trapping these rays within the ring's structure, preventing them from escaping easily into intergalactic space. This creates a radiation environment within the ring far more intense than in a normal galaxy, a factor that could influence the chemistry of future stellar nurseries and the potential for planetary systems. We are only beginning to map this magnetic maze, using radio telescopes to detect the faint synchrotron radiation emitted by electrons spiraling along these powerful field lines. Each new map reveals that a ring galaxy is not just a story of gravity and light, but of electromagnetism on a galactic scale, an invisible layer of physics that turns the ring into a colossal, dynamic particle accelerator. This magnetic maze points toward the heart of the galaxy, where an even more powerful engine may be waking up. At the center of every large galaxy, including these strange rings, lurks a supermassive black hole, a gravitational monster millions or billions of times heavier than our Sun. In the calm of a normal spiral, it often sleeps a quiet titan. But a galactic collision is the ultimate alarm clock. The same shockwaves that create the star-forming ring also funnel colossal rivers of gas and dust directly toward the galactic core, delivering a feast to the dormant beast. As this material spirals inward at near light speed, it compresses and heats to millions of degrees, blazing with radiation before vanishing past the event horizon. This process ignites an active galactic nucleus, or AN, a beacon of fury that can outshine every star in the galaxy combined. The ring's creation may inadvertently awaken a dragon at its center. The AGN's outburst is not a silent feast, it is a violent feedback loop. The intense radiation and powerful jets of particles erupting from the poles of the black hole act like a cosmic blowtorch, blasting back into the surrounding galaxy. This energy can heat the infalling gas to such extreme temperatures that it cannot cool down and collapse to form new stars. In some cases, it can even drive powerful galactic winds, physically blowing the gas reservoir out of the core entirely. This is the black hole's paradoxical role. It can quench the very star formation that its own feeding helped to initiate. In a ring galaxy, this feedback could sculpt the dark gap we see between the core and the ring. The black hole's fury may be responsible for sterilizing the central regions, preventing any late blooming star formation and ensuring the ring remains the sole torch of youth. It is a stunning cosmic balance where the same catastrophic event creates a ring of fire at the outskirts while simultaneously triggering a cleansing firestorm at the center, a dual signature of creation and control written across the face of a reborn galaxy. That sleeping dragon at the galaxy's core is a reminder of how much we have yet to discover. For every brilliant ring we can name, there are countless more hiding in the data, waiting for a human eye to notice them. This is where the story takes a remarkable turn, from distant telescopes to the computer screens of everyday people. The hunt for these cosmic oddities became a global collaboration thanks to projects like Galaxy Zoo. When massive digital sky surveys began pouring in millions of galaxy images, the sheer volume was overwhelming for professional astronomers. They turned to the public, inviting volunteers to become cosmic classifiers. The task was simple but profound. Look at a galaxy and click a button to describe its shape. What happened next was a revolution in citizen science. The human brain possesses an extraordinary talent for pattern recognition, especially for the weird and wonderful. Automated algorithms trained on normal spirals and ellipticals would often dismiss a faint, lopsided ring as noise or a glitch. But a person, perhaps a teacher on their lunch break or a student after school, would see it for what it was, a clue. Volunteers sifting through this cosmic haystack began flagging peculiar rings that the machines had missed. They found delicate, incomplete hoops, galaxies with rings askew, and most excitingly, rare candidates for double rings and polar rings that had slipped through the digital net. Each click was a vote for curiosity, and thousands of those votes added up to real discoveries. Professional astronomers would then follow up on these citizen-identified targets with powerful telescopes confirming their nature. This synergy changed the game. The public became an essential part of the scientific process, extending the reach of a few dedicated researchers into a global network of observers. It proved that the most advanced technology still benefits from a deeply human skill, the ability to recognize the strange, to see the exception to the rule. The Ring Galaxy Zoo, curated by volunteers, dramatically expanded our catalog of these rare objects, showing us that the universe's oddities are even more numerous and varied than we ever suspected. This global network of observers helped map our cosmic backyard, but to see the true origins of ring galaxies, we needed a time machine. The James Webb Space Telescope has become that machine, peering back to an era when the universe was a turbulent, crowded nursery. Its astonishing infrared vision is now revealing ring-like structures in galaxies that existed when the cosmos was only a few billion years old, a fraction of its current age. This discovery is turning our understanding on its head. The early universe was a denser, more chaotic place with galaxies packed closer together. Frequent collisions and mergers were the rule, not the exception. Given that, you might expect to see a mess of tangled, irregular shapes, the raw building blocks of future giants. But Webb is showing something else, galaxies with hints of delicate rings and clean, circular symmetry already in place. This is a profound puzzle. Our leading models for forming a perfect ring, like Hoag's object, often require a very specific, almost surgical collision between two well-developed galaxies. But in the universe's youth, galaxies were smaller, gassier, and more chaotic. How could such a precise, geometric outcome emerge from that primordial frenzy? It suggests that the physical processes that create rings, perhaps through instabilities or particular types of grazing encounters, were operating efficiently and much earlier than we ever thought possible. These ancient rings are not just curiosities, they are revolutionary laboratories. They let us watch the violent adolescence of galaxy formation play out in real time across billions of years. By studying the chemistry of the stars in these primordial rings, we can measure how quickly heavy elements were forged and spread through the early cosmos. We can see if the black holes at their centers awoke faster in these turbulent environments. Each faint, red-shifted ring captured by Webb is a frozen moment from the universe's childhood, proving that even in its most chaotic and formative years, the cosmos had a startling knack for creating order, beauty, and mystery. These ancient rings from the cosmic dawn point toward a hidden transformation happening deep within their hearts. At the center of many early ring galaxies, the James Webb Space Telescope is spotting something peculiar. Not just an old yellow core, but a blazing, sapphire-like knot of furious light. Astronomers call these objects blue nuggets, and they are the hyperactive embryos of future galactic giants. Imagine the core of a galaxy not as a quiet retirement home for ancient stars, but as a frantic, compact factory, churning out new suns at a staggering rate, all squeezed into a region perhaps only a few thousand light-years across. This blue nugget is so intensely star-forming that its brilliant blue light drowns out everything else at the galaxy's center. The discovery of these objects within ring structures is rewriting the life story of the most massive galaxies we see today. That serene, golden elliptical galaxy, the one that might later wear a Seasic ring like a halo, began its life in a state of violent, concentrated creation. The ring galaxy phase appears to be the pivotal moment where this story splits in two. On one hand, the collisional shockwave is building the outer structure, the vast ring that will eventually become the galaxy's extended disk or stellar halo. On the other hand, the same cosmic violence is funneling a torrent of gas directly into the very center, feeding the blue nugget and causing it to swell with new stars at a breathtaking pace. This dual action is building the galaxy from the inside out and the outside in simultaneously. The blue nugget is forging what will become the galaxy's dense central bulge, while the ring is constructing its future outskirts. It is a single, catastrophic event managing two construction projects at once, a cosmic efficiency that shapes the entire future architecture of the galaxy. The ring we see is not just a temporary flash, it is the visible signature of a galaxy being fundamentally remade, its destiny sealed in a single era of glorious, unsustainable fire. But a galaxy's ring is not just a birthplace for stars, it can become a nursery for entirely new worlds. Within the swirling chaos of that collisional shockwave, something remarkable can happen. Dense knots of gas and dust compressed by the passing wave can become so massive and gravitationally bound that they begin to live a life of their own. They are not just stellar nurseries, they are proto-galaxies forming directly from the wreckage of the larger collision. Astronomers call these objects tidal dwarf galaxies, and they are cosmic orphans with a very strange origin story. Picture the vast ring of the Cartwheel Galaxy, a river of gas and newborn stars flowing around the central hub. Now imagine a whirlpool forming in that river, a knot where the current slows and material piles up. If enough mass accumulates in that whirlpool, its own gravity can overcome the tidal forces trying to pull it apart. It condenses, it ignites its own star formation, and it begins to orbit within the ring as a distinct, self-contained system. This is a tidal dwarf galaxy, a new island of stars born not from the primordial gas of the early universe, but from the recycled debris of a galactic car crash. They are typically small, perhaps only a few thousand light-years across, and they often appear as bright, blue clumps embedded within or just outside the luminous ring of their colossal parent. Their existence is a testament to the sheer scale of material displaced in these collisions, enough to build entire new galaxies from the scraps. But these orphans hold a secret that makes them utterly unique in the cosmos, a secret written in what they lack. When astronomers measure the motions of stars within a tidal dwarf galaxy, they find something startling. The visible mass of gas and stars is almost entirely sufficient to explain the gravitational pull holding the object together. There is little to no room for the mysterious, invisible dark matter that dominates every large galaxy we know. This makes perfect, eerie sense. Dark matter is thought to exist in a vast, diffuse halo surrounding a galaxy. During a collision, the visible, gaseous disks of the two galaxies slam together and are flung out to form the ring. But the dark matter halos, being much less interactive, simply pass through each other like ghosts, largely remaining with their original host. The material that gets tidally stripped to form the ring and then clumps into a tidal dwarf is almost purely the normal baryonic matter, the stuff of stars, planets, and us. This purity makes tidal dwarf galaxies extraordinary natural laboratories. They are places where we can study star formation and galaxy evolution in isolation, without the complicating, dominant influence of dark matter. How do stars form in an environment lacking this invisible scaffold? How do these pure matter systems hold themselves together over billions of years? Each tidal dwarf galaxy orbiting within a ring is a controlled experiment, a chance to watch the laws of physics play out with a clarity we rarely find elsewhere in the universe, all born from the most violent of beginnings. This chemical purity in the tidal dwarfs is a fleeting state. As we look inward from those pristine blue clumps toward the galaxy's ancient heart, we find a story written not in light, but in the very elements that make up the stars themselves. Every galaxy possesses a hidden chemical fingerprint, a gradient of metals that tells its life story. In a ring galaxy, this fingerprint is laid out with stunning clarity, from a metal-poor frontier to a metal-rich capital. The term metal in astronomy means something far broader than iron or gold. It refers to every element heavier than the primordial hydrogen and helium forged in the Big Bang. Everything from the carbon in our bones to the oxygen we breathe and the silicon in planetary rock. These heavier elements are not born in the beginning of time. They are forged in the nuclear furnaces of stars and scattered across space when those stars die in supernova explosions. A galaxy's metallicity is a record of its star-forming history, a measure of how many generations of stellar life and death have enriched its gas. In a normal spiral, this history is mixed and jumbled, making it difficult to read. But in a ring galaxy, the violent event that created the ring also organized this chemical history into a perfect radial map. The brilliant outer ring where star formation is happening right now is often surprisingly metal-poor. The gas that was shocked into forming these new stars was recently pulled from the quiet, outer reaches of the original galactic disk, or even from a gas-rich intruder. This material has undergone relatively few cycles of stellar enrichment. It is more pristine, closer to the primordial gas of the early universe. The stars born from it are therefore chemically simple, composed mostly of hydrogen and helium with only a faint sprinkling of heavier elements. Now travel your gaze inward across the dark gap toward the galaxy's glowing central core. Here, the story is completely different. The core is a metal-rich metropolis. For billions of years before the collision, this central region was likely the site of continuous, generations-long star formation. Countless stars lived, died, and exploded there, polluting the local gas with the heavy elements they created. The core's stellar population is therefore ancient and chemically complex, its light tinged with the accumulated wealth of eons of nuclear fusion. What we are seeing is a direct spatial timeline of chemical evolution. The metal pore ring shows us the present-day star formation from relatively fresh ingredients. The metal-rich core shows us the deep past, the accumulated heritage of the galaxy's long life before the catastrophic collision. The smooth gradient in between, if we could measure it star by star, would chart the precise history of enrichment, a chemical clock that corroborates the age clock written in the starlight itself. This metallicity map is a powerful tool for forensic astronomy. By measuring the exact chemical makeup of stars at different points in the ring and core, scientists can reconstruct not just when the collision happened, but what the progenitor galaxies were like. They can ask, was the intruder galaxy a small, metal-poor dwarf or a more evolved spiral? The answer is written in the elemental abundances of the ring's youngest stars, a permanent chemical record of a violent encounter billions of years in the past. That chemical clock is ticking, and its hands move with startling speed. The brilliant ring of fire we marvel at is not a permanent feature, but a spectacular, fleeting phase in a galaxy's long life. According to sophisticated computer simulations, this luminous stage may blaze for only a few 100 million years, a cosmic heartbeat in the multi-billion-year lifespan of a galaxy. The physics behind this ephemeral beauty is a story of energy slowly bleeding away. The initial collision creates a powerful density wave, a coherent ripple of gravitational energy that travels outward through the galactic disk. As it moves, it does work. It compresses gas to form stars. It stirs up the existing stellar population, and in doing so, the wave itself loses energy. Think of it like a ripple in a pond finally reaching the shore, its organized motion dissolving into chaotic splashes. Within the galaxy, the wave's energy is transferred to the stars and gas it interacts with, causing them to heat up and their orbits to become more randomized. This process, called dynamical friction and phase mixing, acts as a brake. The sharp, coherent wave begins to smear out. The ring of intense star formation, dependent on that sharp wave front to compress gas, starts to fade first. The massive blue giants die off in supernova, and without the ongoing wave to trigger new collapses, the ring's brilliant blue light dims, leaving behind a broader band of longer-lived, fainter stars. What happens next is a cosmic relaxation. Over the next billion years or so, the galaxy begins to settle. The once distinct ring structure blurs as stellar orbits intermingle. The galaxy does not return to being a spiral. That delicate structure was destroyed in the initial violence. Instead, simulations show it often transforms into a lenticular galaxy, a smooth, lens-shaped system that blends characteristics of spirals and ellipticals. It possesses a central bulge and a large disk of older stars, but no spiral arms. In other cases, if the collision was particularly messy or involved multiple galaxies, the result might be a peculiar elliptical or an irregular shape, a permanent testament to the chaotic merger. This makes the ring galaxy phase a crucial, transformative but temporary chapter. We are catching these objects in a brief moment of glorious reorganization, a violent storm that clears to reveal a calmer but forever altered landscape. The fact that we see any at all tells us these collisions are not exceedingly rare, but their brilliant ring stage is a blink in cosmic time, a firework exploding in the slow night of galactic evolution. That fading ring of fire leaves behind a hidden architecture, one we can only map by watching the motion of its survivors. The most powerful tool for this task is not a telescope that sees light, but the geometry of the ring itself, especially in those bizarre polar ring galaxies. Their impossible perpendicular orbits act as a cosmic probe, tracing the invisible hand of dark matter. In a normal galaxy, stars and gas orbit within the visible disk, making it difficult to sense the shape of the dark matter halo that surrounds them. But a polar ring is like a glowing test particle flung into that halo's gravitational field. Its entire orbit is a map of the space it moves through. By meticulously measuring the ring's rotation, its tilt, and any subtle warps, astronomers can reverse engineer the shape of the unseen mass that must be there to guide it. The results are startling. A perfectly flat, stable polar ring suggests a dark matter halo that is roughly spherical, its gravity uniform in all directions. But many observed rings are not perfectly flat. They show slight warps or twists. This is a critical clue, whispering that the dark matter halo is not a simple sphere. It might be flattened like a squashed beach ball or even triaxial, shaped more like a cosmic potato, with gravity stronger along certain axes. These distortions in the dark matter's shape imprint themselves on the ring's orbit over billions of years. This makes a polar ring galaxy a unique natural laboratory. We are not just inferring dark matter's presence from missing gravity. We are using luminous matter as a tracer to literally chart its three-dimensional form. Every subtle kink in that celestial hula hoop is a data point, a whisper from the invisible majority of mass in the universe, telling us about the fundamental properties of the substance that shapes cosmic structure itself. While the dark matter halo sculpts the grand orbits, the visible galaxy holds a more tangible kind of shadow. Not every cosmic ring is forged in brilliant starlight. Some are drawn in dust, a silent, cold reservoir that holds the promise of future fire. NGC 1291 presents this very scene, a stunning spiral galaxy where one of its most defining features is not a band of blue giants, but a perfect dark circle of cosmic soot. This is the red ring of dust, a silhouette of fine grains and complex molecules, seen only because it blocks the glow of the billions of stars behind it. It appears as a sharp, shadowy lane encircling the galaxy's bright central bulge, a cosmic smudge ring drawn against the stellar canvas. Its existence tells a quieter, more patient story than the violent collisions that create stellar rings. This dust ring is likely the legacy of a minor merger, a gentle cosmic meal where a small, gas-rich satellite galaxy was slowly consumed by the larger spiral. As the dwarf galaxy was torn apart, its gas and dust, rich with heavier elements, did not plunge directly into the chaotic core. Instead, it was shepherded by gravity into a stable orbit, settling into a vast, circular reservoir far from the center. This ring is now a frigid archive, a deep freeze holding the raw materials for the galaxy's next act. The temperatures here are only a few tens of degrees above absolute zero, allowing the gas and dust to coalesce into dense, cold clouds. These clouds are the essential nurseries for future stars, but the process is slow and quiet, a stark contrast to the frenzied starburst of a collisional ring. This dust ring is a promise of creation deferred, a stockpile of potential waiting for the right gravitational nudge to begin collapsing into new suns. Beyond its role as a nursery, this dark band plays a crucial part in the galaxy's energy budget. It acts as a formidable veil, obscuring our direct view of the brilliant galactic core. The light from the central bulge and any potential activity from a supermassive black hole must filter through this thick screen of dust. The dust grains absorb the shorter, bluer wavelengths of visible light and re-radiate the energy as longer, infrared wavelengths, effectively transforming the galaxy's appearance depending on how we look at it. In visible light, the core is hidden behind a dark curtain, but to an infrared telescope, that same dust ring glows with a warm, faint heat, revealing the hidden energy of the core it obscures. This delicate interplay between shadow and emission makes dust rings like the one in NGC 1291 master regulators, controlling not only when and where new stars are born, but also how the galaxy presents its deepest secrets to the outside universe. The silent promise of a dust ring is a clue to something far grander, a potential key to measuring the universe itself. Could these rare cosmic rings be used as cosmic yardsticks? This is the speculative but tantalizing idea of ring galaxies as standard candles. In astronomy, a standard candle is an object whose intrinsic brightness we think we know. By comparing how bright it appears from Earth to how bright it truly is, we can calculate its distance the same way you can judge how far away a car is at night if you know the true strength of its headlights. For decades, astronomers have relied on certain types of supernova and pulsating stars for this critical task, the very tools used to discover the universe's accelerating expansion. But each method has its uncertainties and complexities. The audacious proposal is that a specific class of collisional ring galaxy, perhaps one born from a very particular type of bullseye collision, might have a predictable maximum brightness. The logic is rooted in the physics of the event itself. If the colliding galaxies are of similar types and masses, and if the impact is nearly head-on, the resulting shockwave and the subsequent starburst might follow a reproducible script. The ring's luminosity at its peak, driven by the frenzied birth of massive blue stars, could theoretically reach a consistent ceiling, a known wattage for this specific cosmic firework. Imagine having a class of stellar explosions that all detonate with roughly the same force. That is the principle at play here. Finding such uniformity in the chaos of galaxy collisions is the monumental challenge. No two galactic crashes are identical. The masses differ, the angles vary, the gas content is never the same. These variables would scatter the true brightness of the rings across a wide range, making them poor standard candles. Yet, by studying large samples with telescopes like Hubble and Webb, astronomers could search for the most pristine, symmetric examples, the ones that look like textbook cartwheel galaxies. If within that most perfect subset, a tight correlation emerges between the ring's physical size, its color, and its total luminosity, a pattern might be coaxed from the noise. Even if they never achieve the precision of supernova, these ring galaxies could serve as a powerful independent check. Measuring distances with a completely different cosmic phenomenon would test the robustness of our entire cosmic distance ladder. Any significant discrepancy between the expansion rate measured by rings and the rate measured by supernova would send theorists back to their drawing boards, potentially revealing new physics or hidden biases in our methods. It is a long shot, but in the quest to pin down the universe's expansion rate, a value with profound implications for its fate, every new kind of measurement is a precious thread of evidence, and the brilliant, fleeting rings forged in galactic violence might just hold one end of that thread. A galactic symphony would play on a scale beyond human comprehension, but if we could translate its energies into sound, a ring galaxy would produce a cacophony of distinct and clashing notes. The deepest, most resonant sound would emanate from the core, a low, steady drone born from the inward spiral of gas feeding the central black hole. This is the base note of the entire system, a vibration measured in millions of years, the sound of gravity's patient, relentless pull. Orbiting this drone, the billions of older stars in the core and the faint halo would create a sustained harmonic hum, a choral backdrop of stable, predictable frequencies, the sound of cosmic order. Against this deep background, the ring itself would scream. The vast, rotating structure of gas and newborn stars would generate a rising, rushing tone, like a cosmic wind howling in a circular channel. But layered over that are the explosive staccatos of creation and destruction. Each brilliant knot of star formation would crackle with the rapid fire pops of molecular clouds collapsing, a sound like static electricity scaled to a galactic storm. And punctuating this crackle would be the deafening, isolated booms of supernova explosions, the sharp, catastrophic reports of massive stars dying. These are the treble notes, the sounds of events that last mere moments or millennia, impossibly brief against the drone of the core. This imagined symphony is not just artistic fancy, it is a direct translation of the different dynamical timescales at play. The deep drone corresponds to the slowest, most massive processes, the orbital periods of stars in the core and the inflow of gas, which can take hundreds of millions of years. The howl of the rotating ring maps to the orbital period of the structure itself, perhaps a few 100 million years as well, but churning with more violent energy. The crackles and booms represent the fastest, most energetic events, the lives and deaths of stars which flash by in just millions of years. Listening to this hypothetical soundscape makes one thing viscerally clear: a ring galaxy is not a single, coherent object moving in unison. It is a collection of separate clocks all ticking at wildly different speeds, a place where the slow, grand rhythms of gravity coexist with the sudden, violent cadence of stellar fire, all woven into one unstable, magnificent whole. That cosmic symphony of gravity and fire is a natural process, but it forces a mind-bending question. Could such a perfect ring ever be a deliberate construction? To explore that, we must step from known physics into the realm of pure, theoretical possibility and scale our imagination to its absolute limit. Consider the Kardashev scale, a way to classify hypothetical civilizations by the energy they command. A Type 2 civilization masters the power of its own star, perhaps by building a Dyson sphere, but a Type 3 civilization is something else entirely. It would command the total energy output of its entire galaxy, a power so vast it borders on the godlike. For such an entity, rearranging stars would be not just possible, but perhaps a trivial engineering task. Could a ring galaxy be the ultimate megastructure, a cosmic signature of intelligence operating on a galactic scale? The concept is staggering. Imagine a Niven ring, a fictional bandworld built around a star but scaled up by a factor of billions. Instead of a single star, a vast, rotating ring of countless stars and constructed habitats, all orbiting in a perfect, artificial harmony. Or picture a Dyson swarm, a cloud of energy collecting satellites, but arranged not around one sun, but in a titanic, galaxy-spanning ring, harvesting light from every star along its circuit. From an unimaginable distance across millions of light years, how would such an artifact appear to our telescopes? It might look remarkably like Hoag's object, a perfect circle of luminous points surrounding a central hub. The central core could be the civilization's administrative or power distribution center, while the ring is its sprawling territory, its engineered ecumonopolies. The dark gap between them would not be a sterile zone left by a shockwave, but a carefully maintained buffer or a transportation corridor. The light from the ring would not be the blue glow of natural, short-lived giants, but perhaps the more uniform, engineered signature of artificial illumination and controlled fusion. Of course, this is the purest speculation, a blending of science and science fiction. No known natural law permits such a structure to be built, let alone remain stable across cosmic time. The gravitational stresses would be unimaginable, requiring materials and physics we cannot begin to conceive, and yet the thought experiment is valuable. It pushes us to look at these cosmic oddities with a new sense of wonder. If we ever did discover a ring galaxy whose properties defied every natural model, whose metallicity was uniform, whose rotation was perfectly precise, and whose light spectrum bore the strange fingerprints of technology, we would have to consider the impossible. For now, ring galaxies remain profound natural mysteries, but they also stand as a tantalizing cosmic template, a shape so geometrically perfect that it makes us wonder if, somewhere in the deep future or in a distant corner of the cosmos, intelligence might one day look at the chaos of a galaxy and decide to draw a perfect circle in the stars. The grandest cosmic mystery might be the one we are inside, as we have journeyed through 24 strange phenomena of ring galaxies, from perfect hoops to violent collisions. A final, unsettling question remains. What if our own Milky Way is not a simple spiral, but harbors the ghost of a ring? Based on painstaking large-scale mappings of stellar motions, a compelling theory has emerged from the data. Our galaxy may possess a vast, faint outer ring structure, a subtle warp or ripple in its outermost disk. This proposed feature is not made of brilliant blue giants, but of older stars, stirred into a vast circle by a gravitational encounter that happened billions of years ago. The prime suspect in this ancient crime is the Sagittarius dwarf elliptical galaxy, a tiny satellite that has been circling and plunging through the Milky Way's plane for eons. Each close pass acts like a stone dropped in a galactic pond, sending a slow-motion ripple through our galaxy's disk of stars. The cumulative effect of these repeated encounters could have shepherded a population of stars into a coherent, ring-like orbit far out in the galactic suburbs. The evidence is statistical and subtle, a slight overdensity of certain types of stars moving in similar paths, a whisper in the stellar census that hints at a larger structure. If this interpretation is correct, the implications are profoundly intimate. It means the majestic spiral we see from within is not the whole story. Our solar system, orbiting safely in a quieter spur, might be situated inside a colossal, billion-year-old ring structure, a fossil of a long-running gravitational dance with a dwarf companion. We would not be mere observers of these cosmic oddities from a distance, we would be living inside one. The phenomenon of the ring galaxy would transform from a distant spectacle into a personal reality, the hidden architecture of our own celestial home. It suggests that the universe's most beautiful and violent processes are not just happening out there, they are woven into the very fabric of our place in the cosmos, a silent, sprawling signature of an ancient collision that shaped the galaxy we call home. From the ghost of a ring in our own galactic backyard to the impossible geometry of polar rings, these cosmic oddities are a testament to the universe's boundless creativity. They are not merely beautiful accidents, they are fundamental experiments in galactic physics, happening on a scale we could never replicate in a laboratory. A perfect hoop like Hoag's object challenges our most basic ideas of formation, while a violent bullseye like the Cartwheel Galaxy shows us destruction and creation are two sides of the same coin. A faint, ghostly ring whispers of ancient encounters, and a perpendicular hula hoop maps the invisible hand of dark matter. Each one is a natural test of gravity, magnetism, and stellar evolution, a unique window into the forces that build everything we see. So the next time you gaze at the night sky, remember that the cosmos is filled with shapes more wondrous than simple spirals. Seek out the images of these ring galaxies. Let their impossible geometry spark your own curiosity. The universe is a grand mystery, and every strange, beautiful object is an invitation to look deeper. If you want to continue exploring the farthest reaches of space and the strangest phenomena hidden within it, subscribe and join us for the next deep dive into the wonders of the cosmos.